So dear student, today we are going to study series parallel operation of SCR, right? As we know that the rating of SCR could be up to 10 kV, right? And current rating could be up to 3 kiloampere. But still there are some industrial application where we required further high rating of voltage and current, right? So to get high voltage we use series connection of SCR, because in series that voltage is divided between the SCR, right? Similarly, for high current rating system, we have to connect SCR in parallel so that current rating could be increased, right? While doing this series or parallel connection, we must ensure that each SCR rating is fully utilized and system operation is satisfactory, right? Here the string efficiency, the string is formed when we connect several SCR in series or in parallel, then a string is formed, and the string efficiency is defined as actual voltage or current rating of entire string, right, divided by individual voltage oblique current rating into number of SCR in string. Clear? So it is quite obvious string efficiency is always less than 1, right? String efficiency is always less than 1. We have to ensure the high string efficiency, but it cannot be 100%, cannot be 1, right? So to get the highest string efficiency, all SCR must have identical VI characteristic. Then only it is possible we can have highest this string efficiency, and this the value of IS is would be 100%, or the you can say the unity string efficiency would be unity if all SCR would have identical characteristic. But this is not possible practically. That is why string efficiency is always less than 1, right? Another point is this, that we must understand that unequal voltage oblique current sharing by the SCR in a string can be minimized by using external equalization circuit. What it means? We have to connect certain resistance or capacitor in such a way that the equivalent resistance of all the SCR is same. So if the resistance offered by the string and the circuit combination would be same, then the voltage would be same, right? So that we will also see in this article. And another thing, by adding an extra unit, reliability is definitely improved, but SCR is derated, and the term which is derating factor DRF is defined as 1 minus string efficiency. If DRF is high, number of SCR has to be increased, right? Now we will see the series operation of SCR. Let us assume we required the string operation, the system operation, we say that V1 plus V2, right? This is the value of this system operation which is required. So we have connect to SCR. Just for simplicity, first we start with 2 SCR, then we will derive the formula for an SCR, right? So here you can see thyristor 1 or T1 and 2 are there, and V1 T1 thyristor 1 suffer voltage V1, whereas thyristor 2 suffers voltage V2, that it shares voltage V2. Why this voltage is different? Because you can see the uh, characteristic of SCR. You can see the characteristic of SCR. Here you can notice that, let me do it for you once again. Here you can see that the thyristor 1 T1 is having voltage V1 for the same amount of current I0, right? So as the thyristor 1 turn on time, or see, we will discuss this dynamic characteristic afterward. Now at present you can see, for the same amount of leakage current I0, thyristor 1 or SCR1 is sharing voltage V1, whereas SCR2 sharing voltage V2, right? So string efficiency would be V1 plus V2, and it is quite obvious we have the rated SCR rating, let us assume it is V1, right, for which each SCR, individual SCR is designed. So total there are 2 SCR, so string efficiency would be V1 plus V2 divided by 2Vn. So you can see maximum voltage is V1 plus V2, not the 2V1. That means your SCR are derated, your thyristor 2 is derated. That is the first thing. So how we can make this voltage sharing equal? For that, the static voltage equalization circuit is used. For that, static voltage equalization circuit is used, right? In this, what we have this n SCR which are connected in series, n SCR which are connected in series, as you can see in the picture. So to share each SCR have equal voltage sharing, we have to connect different resistor across the thyristor or SCR, so that the voltage shared by each device SCR is same. But in that case, this static equalization circuit which we have shown, which we have considered as resistance R for all and SCR, they are different, right? Then only it is possible, because each SCR is having different characteristic. But just for simplicity, we have assumed that thyristor 1 is having one characteristic, and remaining n minus 1 are having same type of characteristic, right? So in that way, we have assumed that static equalization circuit which we have to connect across the each SCR is value R, right? Each SCR is value R. So in that way we are doing this, and practically this solution give the very good result. At the same time, spare management become easier. Why? Because if we consider that across each SCR we will put different register, so that voltage sharing by each register, each SCR and register combination is same. In that case, we have to manage n type of register, which is practically impossible. So because of this reason, we assume that we connect static equalization resistance of value R across each SCR, and the current which is going through SCR1 is minimum leakage current IBMN, and remaining SCR would have maximum leakage current IBMX. Why thyristor 1 is having minimum and why another are having maximum, you can think in clear. So with this assumption we can derive the formula for resistance R. How? As SCR1 has minimum leakage current, so it will block maximum voltage VBM. It will block maximum voltage VBM. Now I1 would be how much? It would be the current flowing through thyristor 1. The current flowing through thyristor 1 is IBMN. So the remaining current, that is I1, which is flow through resistance R, is given by I minus IBMN. Clear? I minus IBMN. So minimum current is passing through thyristor 1 and remaining SCR would have maximum current IBMX. So we can have voltage across SCR1 is VBM, which is equal to I1 into R, and remaining N minus 1 SCR would have N minus 1 times I2R, and string voltage is Vs. So I1R plus N minus 1 R I2 is the total voltage, which is equal to I VBM plus N minus 1 into R bracket 1 minus IBM. After solving this, we would have that RI1 is equal to VBM. So Vs would be N VBM minus N minus 1 R delta IB, where delta IB is IBMX minus IBMN. So we can derive that R is equal to N VBM minus Vs divided by N minus 1 delta IB. If IBMN is not given, in some of the cases IBMN, that is the minimum current, is not given, in that case you can assume it is 0. Always remember this, right? So delta I would be IVBMX as IBMN is 0. Now once you have R, you can find the power of resistance R. Power of resistance R. It is equal to PR equal to VR square divided by R, where VR is the RMS voltage across resistance R. Is it okay? RMS voltage across resistance R. Once again I am repeating the things. As SCR1 has minimum leakage current, so it will block maximum voltage VBM. Now I1 is equal to I minus IBMN and I2 is equal to I minus IBMX, and I is the total string current. Clear? So voltage across SCR1 is equal to VBM, which is of course a maximum voltage, which you can see here. V1 is maximum, right? So why it is maximum? Because the current flowing through thyristor 1 is minimum. So most of the current would flow through resistance R, means I1 would have greater value as compared to I2. So definitely voltage across the thyristor 1 is maximum. Clear? So this is called static equalization circuit. This is called static equalization circuit. You also know that the dynamic characteristic is also different for each SCR. Dynamic characteristic is also different for each SCR. They do not have identical dynamic characteristic. So during turn on as well as turn off, they would have different characteristic. Here you can notice during turn on process, that T1 thyristor T1 turn on first, and then thyristor T2. Here you can notice the moment at T1 when thyristor T1 is on. So voltage across this thyristor is dropped to 0, order of 1 or 2 volt, which we are considering as 0. Here you can see the characteristic. Anode to cathode voltage is dropping and come to 0 for thyristor T1. At the same time, anode to cathode voltage across thyristor T2 is increasing, and entire voltage would be shared by the thyristor T2. Entire voltage would be shared by thyristor T2. So it would share the entire string voltage the moment T1 is on. Right? So the situation is very dangerous because the thyristor is taken for the voltage of Vs by 2. Now it is sharing the entire voltage. So this condition should be avoided during turn on process. Similarly, you can see that for turn off, turn off, turn off, turn off process, you can see during turn off the reverse recovery current that plays very important role. You can see the turn off of thyristor 1, turn off process of T1 is fast. It recover first at instant or first after TQ1 time, right? TQ1 time after or you can see, forget this, recover first. Here I'll show you. Here you can see it recover here at TQ1. The process, the anode current, we know the thyristor is turned off the moment its anode to cathode current is less than the holding current. So here you can see it will start the current this is because of this reverse recovery current, right? So this reverse recovery, because of this reverse recovery current, the thyristor T1 process is it's completely turned off at TQ1, whereas thyristor 2 is not recover not recover. Here you can see it is not recover. So there is accumulation of charge. This accumulated charge, because of difference of this accumulated charge, the voltage across each device would be different. Here you can see, the turn on, during turn on as well as turn off process, in both the cases thyristors suffer from unequal voltage sharing, which you can see here at instant t1. At instant t1, the thyristor 1 is suffering voltage with reference to 0, it is VOB, whereas thyristor 1 is sharing voltage VOB, whereas thyristor 2 is sharing voltage VOC. Similarly, at instant T2, the voltage share by these two thyristors are different. One is sharing voltage VOX, whereas thyristor 2 is sharing voltage VOY. So they suffer unequal voltage sharing during turn on as well as turn off process. The dominant voltage sharing would be during the turn off process. So we design the circuit on the basis of turn off process that will automatically take care of unbalancing during turn on, right? Here you can see, as when both thyristor is recovering from its reverse recovery current, then the current is flowing through thyristor 1 as well as thyristor 2. But the moment, as I told you, T1 T1 is recover first, so it will not allow to flow further current. It will not allowed to flow further current. Not allowed, right? So once it is not allowed, the current will flow through the RC. The current will flow through the RC here, through this path, as well as through this path, which this resistor is for static equalization circuit. This resistor is for static equalization circuit, right? Whereas thyristor 2 or SCR2 is continue to along this thyristor from cathode to anode, right? So for simplicity, let us consider two thyristors T1 and T2. T1 recover first at instant T1, whereas T2 recover after some time. So delta Q, there is the difference between the charge and delta Q for the duration of delta T. So this current would flow through capacitor R. This current would flow through our capacitor C. Now this charge difference create the voltage difference, which is equal to delta Q by C. So T1 share highest transient voltage, let it is VBM, right? This is VBM. Now T2 would share VBM minus delta Q by C. Where this term delta Q by C came? It came from the difference of charge accumulated. Between the two thyristor, right? So Vs would be VBM plus VBM minus delta Q by C. Clear? On the basis of this, you can calculate the voltage share by the thyristor 2 would be half Vs minus delta Q by C. Now let us consider there are n thyristor. So the first one would have maximum voltage VBM, whereas remaining would have VBM minus delta Q by C. Again, for simplicity, we are connecting same capacitor through all the n minus 1. In fact, all the thyristor, just for simplicity and for keeping in the view that spare management has to be very simple. Otherwise we have to have different n type of capacitor we have. So with assume that the same capacitance would be connect across each SCR, and they will give good string efficiency, and voltage sharing would be equalized, means same. So on the basis of this we can calculate the maximum voltage, which is equal to 1 by n bracket Vs plus n minus 1 delta Q by C. So from here we have the value of C. From here we have value of C. Now V2 would be given by Vs minus delta Q by C. So this is the value of capacitor C. This is the value of capacitor C. Right? In this way we can have our static as well as dynamic balancing of this strings thyristor. One thing I would also like to tell you, you can remember that snooper circuit which we have designed. So that snooper circuit is also help for balancing during turn off process, right? And this RC, you must remember why we have connect this RC. It is used to limit the discharging current, because the moment T1 is get on, use current would flow if RC would not be there. So RC would be for that purpose, and to reduce the time constant we connect the diode here. It will bypass the RC during the charging of capacitor. Hope you all remember all those things which we have studied in previous classes, right? So in this way we can calculate the capacitor for static dynamic equalization circuit and resistor for static equalization circuit. Now the next article we will see in our next lecture, which is parallel operation. Series operation we have seen. The parallel operation we will see in our next lecture, right? Okay, bye bye, take care.